My name is Ivan, as most of you know. I am a machine learning engineer at NASA Harvest, and I'll be presenting the crop mapping module, which we have been working on. And so several people have been putting a lot of work into this, including Dr. Hannah Kerner, Dr. Catherine Nakalembe, Gabby who's also a Harvest ML engineer and is currently a grad student at Mila, and Eva, who's a UMD computer science student. So this crop mapping module is kind of a part of this whole process of what NASA Harvest does. NASA Harvest does a whole bunch of work related to applying machine learning to agriculture and going beyond the test metric with the models that we develop. But for this particular presentation, we're specifically going to be talking about the cropland product. And so before we dive into the product, what is a cropland map? So a cropland map is essentially a map that indicates where there's crops and where there's non-crops. So over here, we can see that there's a whole bunch of these squares everywhere. These are most likely crops, and there's some green section that's most likely forest. So if we pass this through one of our models, then we might get an output that looks like this. And so the green sections here indicate the crops, and the yellow sections indicate non-crop. And if we just go back to what it was originally, we can see that this whole kind of green forested section was yellow, and there was also some yellow streaks around here, which look like some sort of maybe roads or maybe some sort of tree boundaries. So this is essentially what a cropland map is, and what is the output of this entire workflow. So we've created quite a few of these cropland maps for different regions. We have examples of a whole bunch of them, and we create them for different regions and for different years too, because depending on the year, a particular field might be planted or not planted. So over the next hour, I'm basically going to go through these four things, and at the end of this hour, I believe you'll all have a fairly clear understanding of what differentiates our approach from other approaches to developing these cropland maps. How exactly we create a map. We'll actually go through a demo of that. How we train a model to make these maps, and we'll also talk about future goals and future directions for this project. So starting with our approach, one of the key differences between our maps and other maps is just the high resolution. A lot of other maps that are made by other groups have a resolution of maybe 100 meters or 30 meters. And that's often not really useful in areas with smallholder agriculture. So in areas where the fields are maybe 10 meters large. Obviously, if the fields are very small, like 10 meters, you're not really going to be able to capture where the fields are if your resolution is set to 100 meters. So we make maps that are 10 meters and that are able to capture a lot of that fine granularity of smallholder agriculture. So another thing that differentiates our approach is that we make region-specific maps. So we develop a specific model and a specific evaluation set for every region that we work on. And in that way, we're able to really optimize the model and make a map that's really has a great metric on that region. And we've done some evaluation comparing some of the maps that we've made to other maps, and have found that we've been getting a consistently high F1 score, which is a metric that we use to evaluate how good our maps are. So we've done this for Togo. We've also done this for Kenya, and this is actually all available in a detailed analysis in the blog post linked at the bottom of this slide. So another advantage of our method is that we have low data requirements. So even though we make region-specific models and we gather region-specific valuation data, we can still use data from other regions. In fact, we can use data from any region in the world, and that's because built into the architecture of our model is this kind of division between a local classifier and a global classifier, which allows us to use and focus on the local region, but still be able to use data from the rest of the world. Another advantage is we have the ability to make in-season maps. So we have a built-in forecaster so that we are able to make maps for the year that is actually occurring. So for example, in 2022, we can create a map, say in August, with only the like, let's say, data from February to August, and then we'll forecast August to February, and in that way be able to create a map for that entire season. And the last and perhaps the most important advantage that our approach shows is we really try to make everything accessible. So all of our code is open source on GitHub, and almost all of the data that we use is available openly through the crop harvest package. So there's actually a link to it right over here. A crop harvest package is basically a Python library that you can easily install in any Python environment. Just run this pip install crop harvest command, and you get access to this global data set of crop and non-crop labels, but also crop type labels. And along with the access to the data, you also get a whole bunch of APIs and functions to process that data, to deal with it, and to create your own data. And so we're actually going to be using crop harvest in the demos because it's super useful for dealing with all this remote sensing data. So that's kind of a couple of things that are different about our approach. To recap, we make region-specific maps that are high resolution. We have the ability to forecast future time steps and thereby make in-season maps. We don't need a crazy amount of data because we can take advantage of data from all around the world. And the last one is that we make everything that we work on accessible, so other people can reproduce it and work on and really contribute to our project. So now we'll talk about creating a map. And so instead of actually talking about it, we're going to go ahead and do it. So I'm going to open up this link. And so this leads me to a GitHub repo. This is the repo where all the code for this crop maps project is. And so if I scroll down, the link led me to this README section, which is creating a crop map. And it says to create a crop map, run the following Colab notebook. So that's what we will do. So Google Colab is a super nice tool for many reasons, but the primary reason that I think it's actually, you know what, I'm going to switch my account first to my UMD account. Primary reason why it's a wonderful tool is that it makes the whole environment setup a lot easier. A lot of the times when I work with Python projects, really any sort of coding projects, it can almost become an entirely separate project of just setting up the environment and figuring out all the dependencies, especially if you're dealing with Windows. Sometimes Windows really is not a fan of some Python packages. And so having this available in Google Colab makes it so that anybody running this Colab notebook is going to get the same results. It's going to be running the same way because this is actually running on a computer that Google has set up for us, and it's completely free to use. So that's nice. The one requirement here that's listed is access to our Google Cloud project. And this is because while we're going to be running the Google Colab notebook, we're actually going to be accessing a Google Cloud architecture that is going to help us generate the map. And we can't give access to that project to everyone because it costs some money to generate the maps. And so if we just give it access to everybody, then everybody can use up our Google Cloud credits, and we don't want that. So what I just did here is I installed some packages to start the creating a map process. And you can see there's a crop harvest over here. And then I'm importing some of these packages. There's some functions that will be used for the purposes of the demo. We're just going to skip through them. They're not super important to understand. We're just going to use them. So here's where it starts to get more interesting. There's this setup button, and it's going to ask me for my Earth Engine username. And this is mine. And then it's going to ask me for the model type. There's two actually available already now. We're just going to use crop mask. That's where we have a lot of models. So once we've inputted the Earth Engine username, we can run this next cell. And then we can run the cell after that to start connecting to some of the services that we'll be using. So the first one is Earth Engine. We're going to be using Earth Engine. Oh, let's see, what is this? Notebook Authenticator. This is some new authentication scheme that they're showing to me. So I'm just going to click on UMD and log in with my UMD account. And so I'm basically allowing, oh, let me see, actually, I don't think that really, maybe I have to generate user read-only scopes, generate token. Yeah, they've added some extra steps for me to get this token. But basically, once I get this token and paste it in here, this means now Earth Engine is connected to this Google Colab notebook. So I can run functions that will trigger Earth Engine, which is important for us getting the right data. And similarly, we're going to connect to our Google Cloud architecture. So this one is not, you don't need any token, you just click allow. And so logged into Google Cloud, logged into Earth Engine. So that's great. And we can close these tabs actually. And so now that we're connected to our Google Cloud architecture, we can see what models are available to us on the Google Cloud architecture. And we can see this list that's available to us. So that's nice. That's what we can use. And we'll run the next cell to actually select the model that we'll use to make a map. One that we made recently is this Ethiopia buried gemma one. And we'll just use the start and end date that are here by default, and a map identifier is needed. So we're going to say maybe demo April 13. All right. Okay, so now we are at this point, there's some red lines over here. And so what we need to do is we need to select some coordinate for which we want to make a map. So I have a coordinate written in the comments over here that I'm just going to pull up. Just got to move this out of the way. So this is for a particular region in Kenya that we did a prior demo for. All right, so what I just did is I pasted in a latitude and longitude, and then I'm going to add a margin to this latitude and longitude, and I'm going to create a bounding box. So this bounding box is basically going to be a 4x4 kilometer region for which we're going to make a map. And so if I click run on this and go down over here, I can see preparing to do inference for this region. And I can check what region, I'm actually, what bounding box I inputted. And if I zoom out, I can see Nairobi. Nairobi's in Kenya. So it looks like my bounding box is indeed correct. All right, so now that I did that, I can run the next step, run inference. And there's a cool diagram here. I'm just gonna scroll through it because I'll go through it in the presentation. So we're just going to go ahead and run this cell. And so now we have this status message over here. All I'm going to read is this last sentence for now, which is waiting for some data to become available. Wait a couple seconds and rerun this cell. So we are going to go ahead and do that. All right. And so now it says Earth Engine tasks 1, data available 0, prediction 0. Please wait for all 1 Earth Engine task to complete and rerun this cell, and then I can view progress here. So we're going to go ahead and open that. And I can see there's something spinning. So this means that something has started happening. So now we'll go back to the presentation while that thing is spinning, and we'll talk about what that actually means, what's happening behind the curtain here. So the way that I like to think about map creation is essentially this equation. You're taking data, you're taking a trade model, you're combining the two, and the output is a map, cropland map. And so what is the data here? The data is a collection of individual pixels, and each pixel is representing a point somewhere on Earth for a particular number of time steps. And so we can talk about the details of what each point represents by expanding out the data that's in each point. So every single point has data from multiple different satellites. It has weather data and it has topography data. So we have data from Sentinel-2, which is a satellite that takes optical imagery. So this is like regular, almost like camera photographs. So some of the bands are actually the regular red, green, blue bands. But we can't just use Sentinel-2 because a lot of the times the areas of interest are going to be covered with clouds. And so if you're just taking optical imagery, you're going to be taking pictures of those clouds, and the clouds are not going to tell you anything about whether or not there's crops growing underneath them. And so for that reason, we also have Sentinel-1, which is a different form of satellite imagery, which uses radar, and it's kind of able to see through the clouds. Weather data is giving us some more information that's relevant for cropland, understanding where cropland is growing, and similarly elevation data. And the last point over here is NDVI, which is the normalized difference vegetation index. That one helps us understand where things are greening up. So for example, NDVI will be very low for a building that has no vegetation growing there. And so for every single coordinate, we have all of this data, and then all of this data is multiplied by 12 months. So we could figure out in theory where there's crop and where there's not crop from just data from 1 month or 1 day even, but it's you're going to be much more confident if you have data over time. Data over time allows you to see crop phenology. So that means when a crop is planted, when a crop is greening up, when a crop is harvested. It allows you to see that time difference. And that's actually the most important thing when you're trying to classify crop or not crop. And so this multiplier by 12 months is super important. And so for simplicity, we're just going to make all that information that we talked about, all those different satellite bands, we're just going to represent that as a single white square. And then our data for each pixel will be 12 of these white squares because we have 12 time steps. And so what we actually started doing just now, when we clicked run on that Colab notebook cell, we triggered an Earth Engine request. We told Earth Engine, generate all of this data in this kind of format, this 12-month format with all those satellite bands, generate it for these 12 months and for this particular region, this particular bounding box that we chose. So that's what the spinny thing is doing. It's generating all of these white squares for that entire bounding box. All right, so that's our data. And then we'll talk about our model. So the model is an LSTM model. We'll go into the details of what that actually means in the training portion of this presentation. All that's important to note here is that there is a local classifier and a global classifier, and that allows the model to focus on a particular region that it was trained on, while also still being able to use data from all over the world. And so for simplicity, we're just going to represent it with this deep neural network symbol. And then now we can kind of show this entire process as a nice pipeline where we start with the region, we specify a region, we send that region to Earth Engine. Earth Engine gives us the data for that region. That data is fed into our model, and our model makes a prediction, crop or non-crop. And so this prediction is just for that single point, crop or non-crop. And this works because at the end of the day, a map is a whole bunch of points, it's a whole bunch of pixels. And we can illustrate that by just zooming in on a point of the map, and we can see all these pixels. And these are all individual predictions made by the model. And so you might ask, can I make this map locally? Why do I need to use Google Colab and Google Cloud Architecture? Why is all this stuff needed? And the answer is you can run it locally, and you can make a map locally, but if you're only using one model, then you're going to be forced to make just single predictions at a time. And that's going to take a long time for you to make a map. It's going to be way too slow. So maybe if you have a more powerful computer, maybe you can run some models in parallel, maybe 4 at the same time, but still that's going to be way too slow. Like, think about this map. It has, a whole bunch of pixels. And so when we're dealing with these millions and millions of pixels potentially for large regions, we have to make predictions with thousands of models. And so that's what we do. And that's what we're able to accomplish with Google Cloud. Right away, we can make predictions for this entire tile, saving us a whole bunch of time. So how I think about this Google Cloud kind of multiplier is if we grab this pipeline from before, we can just multiply this middle section by 1,000. And that means that we go from this single pixel prediction to these large tile predictions, to a whole bunch of predictions at the same time. And so behind the scenes, this is what the multiplier looks like. The Google Cloud Architecture, which is the multiplier, receives data from Earth Engine in a Google Cloud storage bucket. And this is advantageous for 2 reasons. First of all, it's just a very, Earth Engine and Google Cloud are both made by Google. So this the sending of data is fairly seamless compared to using other cloud services. This kind of arrow would become much more complicated. The other advantage is that the amount of data that we're exporting for a country like Malawi, for example, we are using more than 1 terabyte of data. And so it's infeasible to store that locally. It's infeasible to store that on some hard drive or some virtual machine. And so storing it in a data storage bucket is really the most cost efficient and really the easiest way. And so that's the first step of the process. This data gets exported to a data storage bucket. And once the data arrives in the bucket, it triggers the Google Cloud function, which sends a request to Cloud Run. And Cloud Run is where most of the magic happens in this architecture. Cloud Run is kind of the multiplier effect that multiplies our model by 1,000 times. And the way it does that is that we'll go to the bottom of this. We take the model that we trained, and we take an optimized version of it. So we take a version that kind of runs super fast, and we package it into a torch server. So that's a way to expose it through HTTPS or HTTP requests. And then we package this server into a Docker container. And this Docker container is deployed through Cloud Run. And then this Cloud Run service is able to multiply this Docker container multiple times. And each Docker container has all these optimized models. And so these models are then kind of multiplied multiple times. And then these models also inside this whole kind of Google Cloud Run Docker container, once the model makes a prediction, it automatically uploads it to a separate bucket. So we have a separate bucket for storage of the predictions, and those predictions take up much less space because the predictions are just float values from 0 to 1. And so they don't take up as much space as all the remote sensing data. And those predictions are what's going to help us make our map. And so the nice thing about this is that when all the data is available, then this architecture can process more than 1 terabyte of data in 18 minutes, which is super nice because if you do this kind of work sequentially, you know, on a local computer, on a virtual machine, this is going to take much longer, perhaps in the magnitude of days or even weeks. All right, so we can check our inference progress now. So we're going to go back to the notebook, and the last thing that was said was, please wait for all Earth Engine tasks to complete and rerun this cell. View progress here. So we're going to rerun this cell and see what is happening. All right, so Earth Engine tasks 0, data available 4, predictions 4, inference complete, time to merge predictions into a map. Perfect. So looks like this whole kind of pipeline worked. So there was data that flowed through, there was predictions that were made, and now they're available. But these predictions are all kind of separate. All these pixel predictions are not attached together. And so what we're going to do next is we're actually going to merge them into a map. So we're going to run these next cells to first download the predictions over here locally to Colab. It says may take several minutes. If you're making a map for an entire region, it'll take that long. Since we're making a small bounding box, it took like a second. So we download all the predictions, and these next two cells combine all of them together. Went super fast because it's not a large region, but even for a large region, it's not going to take a crazy amount of time. And so once we have these, you know, we've merged this, we merged all these predictions into a map. We're going to upload it to Google Cloud and then send it to Earth Engine to visualize. Earth Engine is a great tool for two reasons in this context. One is for getting the data, two is for visualizing the data. And so we just sent our map to Google Earth Engine, and the map app upload has started, and we can see the map upload in the Earth Engine tasks. So if we open this up, we can see this was the previous task that we ran to get the data. This one has a check mark. This is a new task that we're running, which is ingest image, and it has a spinny thing. So so it's being uploaded, and so we will let that run. It should take less than a minute. But something to mention here is that at this stage, once we did the merging, we actually have the map also available in Google Colab. It's right over here. So for people who have used QGIS, for example, you could download this from here and view the map in QGIS. But we prefer using Google Earth Engine for this, because using Google Earth Engine means nobody has to make sure they have enough space on their computer when dealing with large maps. And it's super easy to share the map because you don't have to send these entire files. You can just share a link to the Google Earth Engine asset. So we can see what stage this is at. We might have to reload. Looks like this is still loading. So I think what I'll do quickly is I will just show you what crop harvest looks like through this link. So crop harvest was the package that we used for dealing with the data. And so here's a link where it's available on the Python package index. And so there's a README about how to use it here, and with all sorts of details. And if you click on the home page, it's going to lead you to the repository. And so this is an open source project that really anybody can contribute to. There's existing issues that you could take a look at and potentially help with. And there's also a whole bunch of documentation related to demos. So for example, there's a demo about using the crop harvest package, the crop harvest data when training a model. There's a demo for exporting the data. All of this is easily accessible. All right, so let's go back to our Earth Engine task. And all right, so it took 2 minutes this time to upload. It's a little longer than I expected, but that's fine. So we will click View Asset on this. And the reason I know that I need to click View Asset is because that's the instruction written over here in number 6. And then it says click Import. And so if I close this up and I have this page, there's an import button. So I'll click that. And then, oops, close this. It says to Actually, it doesn't say, it just gives me the script to copy. And that's what I'm going to do. I'm going to copy the script over, and that's what's going to help me visualize this map. So the first lines here are just loading in the color palette, so the map is not black and white. Then we need to set the center of the map. So we actually need to set these longitude and latitude variables, but thankfully we have them up over here. And we would paste them here. Because we're dealing with JavaScript, we gotta add a var. And I think the zoom level is probably fine. So we're just gonna go ahead and click run, and I'll explain what the rest of the things here are doing. The other lines over here are adding this image. There's an image added that's a mask, and which is just threshold, which is our predictions thresholded to have 1 if they're over 0.5 and to have 0 if they're under 0.5. And there's one that is the float value predictions. So all the ones from 0 to 1. So here we go. We'll click satellite view. We'll maybe do full screen. And we will zoom in. Oop, maybe that's too much. All right, let me move this out of the way. Some zoom thing. Okay, so just to demonstrate here's the float values. So you can see there's a range of values here. The ones that are super yellow are 0, and most likely the model is saying these are non-crop. The values that are super green or super dark really are the values that the model is very confident in, that they're crop. And so if we threshold these values with the mask, we get this, which is a crop mask and the name of the repo. And we can zoom in and check the quality of this in some areas. For example, we can see all this green stuff over here, and we can kind of make it transparent, and we can see that in this particular area, it looks like there's a lot of fields. And if we visualize it with our mask, we indeed see some green there, which means that our model predicted it was a crop. And then in these areas where there's some shrub-looking trees and yeah, I really like trees growing all over the place, it looks like the model predicted yellow, meaning non-crop. So that's great. And one thing to note here, though, is that this satellite imagery that we're looking at is not necessarily for the same year that we made the map for. So we made the map for the year 2020, but the satellite imagery might be from 2022 or for 2010, maybe even. So to be to do a serious analysis, you'd have to load in the satellite imagery from the proper year. But for demo purposes, it's fine for us to just evaluate or qualitatively evaluate using this particular satellite imagery. So there's some more fields over here. Maybe we can look at the actual predictions now instead. Let's see. Oh, sorry. Actually, I went a little too high. Here they are. So some more green stuff over here. And yeah, it does indeed look like fields. And keep in mind, this is made using a model that was trained for a different region. But for demo purposes, we demonstrated it on a region that it wasn't trained on, but it still performed decently. If we were to actually work on this particular region, we would develop a region-specific valuation set, a region-specific model, and we'd probably get even better results. So, oops, I didn't mean to stop sharing. But that's essentially the first part of this presentation, how we create a map. Any questions? If not, I'll move on to the next section. Okay, so the next section is training a model. So we had this equation for creating a map, taking data, taking a trained model, combining the two, and we got our map. But how did we get our trained model? We kind of glossed over that portion. That's what this section is going to be about. It's going to be about training a model. And so we're going to do a similar kind of process, which is actually doing it. So we'll close this other, these tabs that we don't need anymore. And we followed the link and it led us back to the repository. And this time it led us to this section, training a new model. And so there's also a Colab notebook for us to run. So we're going to go ahead and open that Colab notebook and start doing things. So let's see. Standalone notebook for training crop mass models. And the first cell, it says, if you don't have one, obtain a GitHub personal access token using the steps here. So we're actually going to be cloning the repository into the Colab notebook environment. And so to clone a repository, you now need to have a GitHub personal access token. You also need to have a GitHub account. And that's what I'm inputting right now is my GitHub information. And then I have a GitHub token. Go ahead and copy it, paste it in here. And we are starting to clone the crop mass repo now into this environment. So that's neat. And the same way that we did for the previous notebook, we're going to set up our environment by pip installing the necessary packages. You can see there is the crop harvest one over here. So it's going to be used during training as well. And you can see there's another package over here that I want to touch on. It's DVC. DVC stands for Data Version Control. And it's a package that we use for keeping track of all of our training data. We have a lot of training data that we're using for all these different models, and we're constantly updating it, maybe cleaning it, removing examples that are incorrect. And so version tracking all of those, versioning all those different modifications to the data set and additions to the data set is important. And this package makes it easy for us to do that. All right, so looks like we've installed the packages. There is some warning over here, but if we run this unit test and it passes, then we don't have to worry about that. It's most likely just some issues with versions of different packages. And so looks like all these tests pass. So we're going to go ahead and press on. Okay, so we are asked to, we import some of the necessary packages here. And then we're going to log into a service that is new for training. And the service is called Weights and Biases. So this is a service that's very useful for keeping track of all the different training runs that we have. I'll demonstrate it once we actually get the training underway. We need to connect to Google Cloud to actually download our training data. And so using DVC. And so that's what we're doing over here. And this next cell is actually downloading all the latest data. So you can see there is models being downloaded, there's process data, there's compressed features, and then these features are being uncompressed. So that's what's happening right now. You can see that nice green arrow. It's saying which command the Colab cell is currently running through. So we just downloaded all the data that's necessary. You can actually see it if we open up the file view, and here's the crop mask repo that we cloned. If we open this up and open up data, we can see there's features, models, processed, all these folders. And if I showed you this folder before, you'd see that these didn't exist here, but I didn't do that, so you'll just have to take my word. So next, we will see what models are already available. So we have this list of models, and we will also see which data sets are available for us. So there's a whole list of data sets and some information about them and their splits. We're just going to scroll through this because we can talk about it in the slides, but if you didn't have the slides, then you could look at this in more detail. Okay, here are some diagrams about the architecture. We will talk about these in the slides also, so we'll scroll through them. All you need to know or remember is that there's these two heads of the model. One head is for local data and one head is for global data. So basically the model needs to be shown where it should focus. And we do that by specifying a bounding box. We basically give it a bounding box and say, focus on this region. Points in this region are important. Everywhere else, points are still relevant. You can still use them to train, but they're not the important ones. And so here's some bounding boxes that are available by default. You can create your own. For the purpose of the demo, we're just going to use one of the default ones, which is East Africa. And then we are going to run this cell, and we need to come up with a model name. It gives us a suggested format. Since this is just a demo, I'm going to say demo model April 13. And evaluation data sets. I need to select the data sets which are going to be used for evaluating. I'm going to use some examples over here. And there we go. Okay, so this is the absolute basic configuration that you need to have model training going. There's a whole bunch of other parameters and hyperparameters that you can set, but we'll stick with these model name, evaluation data sets, in the bounding box. And so if I click this next cell, this is the one which starts the training. You can see the bounding box is inputted as separate coordinates. There's a model name, evaluation data sets, and there's some max epochs, and it says 3. This basically means how many times the model is allowed to run through the training data set. So to basically not spend too much time training, it may take up to 30 minutes sometimes. Usually it takes up maybe 15 or 20. But to keep it short for the demo, we're going to limit it to 3 epochs. So it's only going to run through the training set 3 times, and that's it. All right, so while that training is happening, while something is, caching files is happening, we can go back to the slides and talk about what the script is doing. Okay, so I have another equation for the trained model this time. And the trained model I like to think of is essentially a combination of labeled data and model architecture. And so we can talk about each individual one here also. So the labeled data, we can recall we have that point, and the point, each data point is a coordinate somewhere on the Earth, and it has all these different satellite bands and weather information and NDVI, and all this is multiplied by 12. So we have all that information, and we represent it with those white squares, and the white squares span 12 months. So there's 12 of them. The one difference with labeled data is that now for every point that we have available, we have a label. So a label basically means that this one pixel with this data over 12 months is either crop or non-crop. It either has crops that are growing there, or it doesn't have crops that are growing there. And so this particular one, you can probably see that, looks like some sort of field over here. And so we're going to label this point as crop, and I'm going to represent it with this green square. And the way that we do this is through Collect Earth Online. Some of you probably have done some labeling, and a lot of those labeled points are currently being used in our training data, in our evaluation data. But the way that we generate them is we have this platform where we're able to look at points and browse for a given point, browse at how it looks like over time, and then label it as either crop or non-crop. So this one would be labeled as crop, for example. And then we combine a whole bunch of these points for a particular region, and we get a data set. So here's an example of a data set for a region in Ethiopia, C-grade 2020. And so you can see there's a whole bunch of green and yellow points. The green points represent points where there's crops, and the yellow points represent points where there's non-crops. And each of these points has those 12 months of data. And so we'll represent each data set as this kind of gray data set. So in our repository, we currently have a whole bunch of these available labeled data sets. We have some that are global. Actually, the biggest one is global. It's a GeoWiki Land Cover 2017, and a whole bunch from different countries in Africa. So for example, there's one from Ethiopia. We have one from Argentina over here. And so we can use all these different data sets for training. And this whole process works because we're able to focus on a particular region, but still use data from other regions. So that's the labeled data. It's a collection of all these different labeled data sets. And for model training, for machine learning, you need to split your labeled data into training data and evaluation data. So we'll talk about that briefly. Evaluation data has kind of a key condition, and that is that it must be representative. If your evaluation data is what you use to figure out if your model is doing a good job or bad job. But let's say if all your evaluation data for this crop mapping module was inside a city, probably all of that data will be non-crop. And so if you get all those points right, if you guess all those points are non-crop, that doesn't necessarily mean that your model is going to do well on more rural areas. And so your evaluation data must be representative of the region of interest that you're making a map for. So if you're making a map for all of Kenya, you need to have points from all over Kenya. The way that we gather this representative sample is we do a random sample across the region of interest, a random simple sample. That sort of method just allows us to generate labels in a fairly fast way. It's also possible to do with a random stratified sample, but that requires a significant amount of additional work that slows down labeling significantly. The evaluation data should have a similar crop percentage as the region of interest. And we've done some analysis and found that we need at least 525 examples in our evaluation data to have some confidence about the metric on our map. You know, if you only have 10 points in your evaluation data set and you get all of them right, you're not going to have high confidence that your map is going to be great. But if you have a lot of points in your evaluation data set, the more you have, the more confident you can be. Training data doesn't have that many requirements. The only thing to note is that some training data sets will be very relevant because they'll be local, and some data will be less relevant, but will still be used because it's global. Okay, model architecture. So this is what the model looks like. It's an LSTM network. So that is a long short-term memory network. And it's particularly good for time series data. And here we're dealing with those 12 months of different remote sensing data. And so it's well suited. And it has been used for quite some time. And it's not super large in that, so it can fit into our whole architecture fairly nicely. So this makes it very suitable for this particular project. But the main thing to note is the local and global classifier, which allows us to make use of all the data we have available while still focusing on the region of interest. Okay, so briefly, we'll just go over what's actually happening when we click train, when we start running that training script. We have our training data, we have our model architecture. What is happening now while we're kind of sitting here, what that Google Colab notebook is doing is it's taking an example from the training data. So each example, remember, is that crop or non-crop pixel with all that data. It's splitting the label and the remote sensing data, and it's feeding the remote sensing data into the LSTM model. So every white square, which represents a separate month, is going to go into a separate input in the LSTM. And it's going to go through all the way through this model and make a prediction. And so in this case, we'll imagine that the training data was local. And so the prediction that we will care about is the local prediction. And so this is where the label comes into play. We can take our label and we can make a comparison. What is my prediction and what is my label? So if our prediction was non-crop, but the label was crop, the model did a bad job. And so we tell the model, you did a bad job, you need to change yourself. And what the model does is it uses backpropagation to update its weights. So there's all these different weights inside of this model that help the model make a decision whether something is a crop or not crop. So it's going to change these weights if it made a wrong prediction. If it made a correct prediction, if it guessed crop and the label was in fact crop, then we can tell the model, nice, you're doing a good job. It doesn't really have to change that much. And in fact, when it starts to make a lot of good predictions, it's going to stop training because we've got a well-trained model. We also have the evaluation data. So the evaluation data is used in a similar way. There's just one key difference. The data is fed in the same way. The comparison is made the same way. But this time, if we made a wrong prediction, we're not going to update the weights. Instead, we're going to write that down. And we're going to track how many wrong predictions we made and how many right predictions we made. And we're going to track that in the form of a metric, like the accuracy or the F1 score. And so this is useful because we kind of get an unbiased look at how the model is doing. So that's kind of what this equation looks like with some diagrams. You got your training and evaluation data. You give that to the model architecture, or you combine both of those together. And after some training iterations, after the training data is passed through multiple times, the model eventually starts doing a better and better job at predicting crop or not crop, and you get a well-trained model. All right, time to check what's happening in training. Okay, so check mark. So it looks like this is done. So we can see there's some results and a whole bunch of logs. So we can read through those, but instead we'll click on this weights and biases link, which is going to give us a nice, much more visual interpretation of what was going on. So there's a loss curve over here, which represents the training loss and the validation loss, which is what the model was using to assess its performance. The lower the loss, the better. And so we can see the training loss going down. We can see the validation loss slightly going down. We only ran it for 3 epochs, so there's not that much data here. But here's the validation loss individually, and we can see it's going down. We can see the F1 score is going up, so that's cool. And we can look at some other metrics over here, but we will not. This is just one of the benefits of weights and biases. The other benefit is that we have all the different configuration things, that all the different parameters that we have set for this training are tracked over here. So before I show you this, one thing that I used to do prior to using this tool was when I ran a model, I would write down the different parameters that I set. I would write down valuation data sets that I used. I would write down maybe the bounding box that I used, maybe the number of epochs that I was using. I would write this all in a Google Sheet, and then I would, over time, I would have all these model runs, and I'd be able to do some analysis. Weights and biases does all this automatically for me, so I don't need to open up Google Sheets, which is very nice. So you can see there's things like batch size recorded over here. If we search eval data sets, we can see eval data sets and the ones that we inputted. So this makes it super easy for me to track all of this configuration information. And what's nice is that it also makes it easy to look at this run in comparison to previous runs. So I have 248 runs total in this project. A lot of the last ones are demos. And I can open up a table view and look up maybe, oops, sorry about that. I can look up, particular, for example, evaluation data sets. I can sort by them or group them together or filter by them, for example. And that makes it easy for me to kind of, look at F1 scores or look at how many minutes things took to train. So just simplifies a whole bunch of work that I previously had to do with Google Sheets or with some other recording tool. So that's how I keep track of this model training. But what actually, what this script did is that it created a model. And so if we run this get model names script now, we can see there's all these models that were there before, but there's this additional model that we just made. So that's nice. And you can actually see it in here. Right over here, there's a demo model April 13th .ckbt. This is a checkpoint model, and then .pt. This is the optimized version that's going to be deployed. And so the next steps is pushing the model to the repository. So we're going to first commit it to DVC. So we're going to kind of use the data version control tool that I talked about previously. And so that is done. And then we're going to create a pull request to basically push this model to the repository. And so I'll click on this link and I can have this new pull request over here, and I can click create pull request. And there's at least one review required. And I can take a look at what files are changed, and I can see that there is the DVC file is updated. So my model will be available to other people using DVC once this is merged. And there's also validation and test metrics recorded, and a link to weights and biases with all the parameters. So that'll be nice for tracking later on. And what has also started now is there's a Git Guardian security check, but there's also a test. So what this means is that the change that we just made, before being allowed to merge, has to pass through a series of tests to make sure that the model actually works as intended. And so that's what's happening now. And if actually, so that maybe takes 5 minutes, so I'm not going to wait for that to finish. Instead, I'll just show you what the finished ones look like. So there's two green buttons over here. One is test and one is deploy. If I click the test one, that shows, here's the one that we have running right now, but here's a previous one. Actually, this was submitted by Eva, and we can see it passed a whole bunch of tests. There's a whole bunch of check marks, and some of them are something to do with integration tests and model results being consistent. So things are looking good in this particular test. The other green button was deploy, and that one I'll just briefly talk about in the presentation. Okay, but that was we just trained a model and we just pushed it to the repository. So if we merge it, what's going to happen is that it's basically going to go from this equation that we just talked about. It's going to float down into this equation that we talked about at first. So we just use label data and the model architecture, combine those two together, and we got a train model. And now, once it passes all these tests, it's going to go into the deploy action, and it's going to be deployed into the Google Cloud architecture. It's going to be packaged in the Docker container, all those things that I showed in previous slides. And it's going to be available next time that we run the inference notebook. And here's a visual representation of all of this. The main thing is just that the train model goes from here to here into this bottom pipeline, and we're able to use it to create a map. Okay, so last thing I will talk about is future goals for this project. Our future goals are increasing the labeling and data collection workforce. The main input for creating well-trained models is good training data, and so increasing the amount of people and how we do labeling is very important for us. Another future goal is addressing common model failure modes. So actually evaluating how well our models are doing and diagnosing why they are doing poorly or why they are doing well is an important future goal. And the last one is incorporating crop type models. You saw that there was that crop type radio button available. We just have one demo model deployed right now, but soon we will have crop type models that are available for making these sort of maps as well. And here's just a few ways that other people could contribute. First, and probably the simplest one, is by labeling remote sensing data. So it doesn't take a whole bunch of work to learn how to use the Collect Earth online tool and be able to label data for us. And that label data is super useful. So that's one way that people can contribute. Gathering ground crop type data is is another way that people can contribute. We can't collect crop type data the same way that we collect crop non-crop data, because it's harder to tell using remote sensing data. So gathering it on the ground is something we can use help with. Providing feedback on our map products is another way that people contribute. Providing feedback on the Colab notebooks, they're very much in beta stage right now. And the last one, and I think perhaps the most relevant for this audience, is contributing to workflow iterations, contributing to the actual projects. So I'll just quickly actually show the repository. If I go back to the repository, there's 19 issues here at the top. And these issues are almost like entire projects in itself. And so they have different labels, and there's some that are labeled good first issue, which are perhaps a little bit easier to implement. And so this is ways that anybody can contribute to this project. All you have to do is basically open up an issue, take a look at what's written. If you read through the description, you can see if this is an issue that would be fitting for you to work on. And then you can make a pull request, and that's one way that you can contribute. And that pull request will be reflected in your public GitHub profile, and you can tell all your friends about it, and it'll be super cool. So that's the last way to contribute. So that's the presentation. I hope you learned how our end-to-end workflow for generating high resolution cropland maps works. Thank you.